So it's 9 o'clock East daily saving time. Anastasia, are you ready? Okay, so let's roll. Let's see here. Okay, good morning, good afternoon, and good evening. Welcome again to the World River and Delta Source to Sink webinar series. And today is number 29 of this year, 2021. So we invite Dr. Anastasia Flores from Los Alamos National Lab come here talk about the Arctic Delta, not only one river, a bunch of the river and the delta. So we get the whole package. That's a very good deal. And before I introduce Anastasia, I want to mention this coming Friday. This Friday, same time, we have Professor Gil Carnegie from Boston College come here talk about flu Mars. She will cover a couple case studies all the way from Amazon shelf, Yale River, Falaya, and couple other places. So please mark your calendar. So nowadays we have heavily to rely on our calendar. So we're living for calendar, looks like. But anyway, Anastasia, as I mentioned, is a research scientist from Los Alamos National Lab. And before that, she was a postdoc over there. And also she got a PhD from UT Austin. And in this talk series, we have I think more than almost 10 colleagues either graduated there or working there. UT Austin, we know, have a fabulous, fantastic, geoscience program. And so she got his bachelor from UPenn geology program. So her research is a physical experiment modeling fieldwork and focus on the formation of, the morphodynamic, the fluvial delta and the coastal system, and also interaction with vegetation, hydrology, climate, and the surface process. So I think we'll go ahead. Anastasia, please go ahead to share your screen, and we're looking forward to your talk.
Great, thanks, Paul. I'm gonna start. Oh, that happened quickly. All right, do you see a large delta? All right,
very
great.
Good.
Great, yeah, thanks. So I'm gonna dive in here and talk about some work we've been doing to try to understand the morphologies of Arctic deltas and also the processes that shape them and that affect their dynamics. So for those who don't work in the Arctic, I'll start with a little bit of an Arctic introduction here. So the Arctic Ocean is pretty small. It holds only about 1% of the world's seawater, but it receives more than 10% of the world's riverine freshwater. So you can see that there are a number of really large rivers here that drain the northern slopes of continents. They pump a bunch of fresh water, but also nutrients, sediments, and heat into this pretty small Arctic Ocean basin. And so over time, this really large river influence has contributed to a slight warming and a slight freshening of the Arctic Ocean. We know, though, right, that the rivers are not pipes and they interact with the landscapes around them. And at the mouths of rivers sit river deltas, which kind of complicate that land-ocean connection because deltas can alter the timing, the location, or even the magnitude of some of these land-ocean fluxes, depending on the transport pathways that water takes through the system. So this figure here is from a paper by Matt Hyatt and Paula Paslakwa, some were UT Austin colleagues, that kind of shows some of the different possible transport pathways through river deltas. So you could have water and its constituents just moving through this main distributary channel. That'd be pretty straightforward and pretty fast. But you could also have water moving into these smaller secondary channels. Some of those might be bidirectional. You could have overbank flow that then deposits sediments on the delta plain, so that reduces the sediment load to the coast. Water could move into these wetlands or even lakes, so you could have transient or permanent storage that alters the residence time and then the nutrient fluxes. So overall, right, these transport pathways, they alter those coastal fluxes, the fluxes to the coastal ocean and eventually out into the Arctic Ocean. So there are, effects on the sediment transport and aggregation, or the overall dynamics of the river deltas, depending on where sediment gets deposited, but also effects here then on the nutrient load. So there could be even some larger scale feedbacks where deltas control the amount of nutrients getting out to coastal ecosystems that affects things like marine primary production and climate. So these are really important to understand in Arctic deltas, or in deltas in general. And understanding these transport pathways really requires us to understand the morphologies and the dynamics of river deltas. Now, many of you have probably seen this diagram, but typically, right, we talk about delta morphology and dynamics in the context of this ternary diagram that describes the relative influence of rivers, waves, and tides on deltas. But we know from some more recent research that people have pointed out things like grain size, basin depth, basin slope, vegetation, or just the overall amount of cohesion can also affect the dynamics and morphologies of deltas. And climate also has an effect. So climate, right, is going to affect the balance of these three large drivers of rivers, waves, and tides, but it also affects the local conditions. And in the Arctic, it leads to this unique formation of ice and permafrost on river deltas. So on the left side here, I'm showing a map of Alaska where people have mapped out or estimated the likelihood of near surface permafrost. So permafrost, for those who are not familiar, being ground that remains below 0 degrees C for a minimum of 2 years. So it never gets above 0 degrees C for within a 2-year period. And here we're looking at near surface permafrost. So permafrost in the upper meter of soil, so likely has some sort of effect on things like channel dynamics on deltas. So we've got the absence or presence of near surface permafrost in Alaska, and I've added onto this map the locations of the Yukon Delta here in southwestern Alaska, and then the Colville Delta here up on the north slope. So you can see that the Yukon Delta, the near surface permafrost is pretty patchy compared to something like the Colville Delta that is entirely underlain with near surface permafrost. But we have no understanding of how the presence of permafrost, let alone the extent of permafrost, affects things like sediment transport and channel dynamics in these systems. Now on the right side of the screen, I'm showing part of a Landsat scene of the Lena Delta, and this scene was captured on the day of peak flow in 2015. And all this bright blue that you see in here, this is ice and snow. So the day of peak flow in June, we've got over 150,000 cubic meters a second of water coming down the Lena River to a largely still ice-covered delta. What effect then does this ice cover have on patterns of sediment transport and on the dynamics of the system? We don't really know. So today we're going to look at Arctic deltas and try to understand their morphologies and how much their morphologies vary between systems, whether or not that morphology tells us something about delta dynamics and also those coastal transport pathways, right? The delivery of water, sediments, nutrients, and to some extent heat. We'll also try to tease out some of the influences of these uniquely Arctic variables of ice and permafrost on delta dynamics and morphology, and then think about how Arctic deltas might change as the Arctic warms, right? As the influence of ice and permafrost decreases and those things go away, and how resilient then will these systems be to possible sea level rise. So to do that, we're going to use this combination of remote sensing based observations and some numerical modeling. So we're going to start with the remote sensing and use remote sensing from Landsat, in this case, just multispectral imagery, to quantify some different aspects of delta morphology. We can also pull, though, from other people's observations of the effects of ice and permafrost on these systems to try to understand parts of that morphology, and then use those observations to inform a model to look at the effects of permafrost and ice on larger scale, longer term landscape change. So then from the modeling, we can infer the effects of permafrost and ice on delta morphodynamics, but we can also infer these future delta dynamics as the Arctic warms. And then finally use those modeling results to better understand our observation-based analysis and the relative influences of ice and permafrost on Arctic deltas. So I'm going to start with the remote sensing, and that's going to be, I think, most of the talk, and then I'll get to some modeling towards the end. So we did this remote sensing analysis focusing on 6 of the largest Arctic deltas. So we've got the Colville Delta, which is on the north slope of Alaska, the Yukon in southwestern Alaska, then the Lena, the Kolyma, and the Yenisei are all Russian deltas, and the Mackenzie Delta is in the Northwest Territories in Canada. So we pulled Landsat-8 imagery for these 6 systems, and we're using just late summer imagery. So the systems are frozen, they're covered with ice for 7 to 9 months of the year, and then they have a really drastic spring flood that happens end of May, early June. So there's really a narrow window of time where we can look at these systems with multispectral imagery when they're not covered with either ice or water. So we're pulling late summer imagery. We use that in combination with eCognition, which is an object-based image classification software, to classify the land, channels, and lakes. And those classifications are what you're seeing on this slide. Anything that's yellow, these are what we're calling small water bodies. So the yellow small water bodies are not really included in our analysis. So these are areas where it's hard to tell if it's really water at the resolution of Landsat, or if it's permanent water. It could just be sort of intermittent flooding, or maybe some wetlands that show up as wet but aren't really a standing water body. So then we take these classifications and we use them to quantify a number of metrics that tell us something about delta form and function. And I'm going to walk you through just a handful of these today that I think are particularly insightful. So I'm going to start pretty large scale here by looking at the delta islands. So here you're looking at maps of all the islands that make up each delta. And the islands here are colored by their size, but we've normalized it by the total delta area. So you're looking at each island size as a fraction of the total delta area. Now, the distribution of island sizes, it tells us something actually about the channel dynamics. So active channels tend to create new islands. New islands tend to be smaller, right? These new deposits. So those would be red on this figure. And then parts of deltas that have maybe less channel activity currently are likely to have larger islands. So that tells us that maybe there haven't been any recent avulsions to that area, but instead that could be an area that was recently abandoned by an avulsion or abandoned by the active channel network. So you can see that, of course, there's some parts of some deltas that have some of these larger islands, so we can sort of start to tease out what part of the deltas might be more active than others. But hopefully something else also jumps out at you right away, which is that 3 of these deltas, which are the Lena, the Mackenzie, and the Yenisei, they are all red. They have all of these smaller islands. The other 3, right, the Colville, the Kolyma, and the Yukon, these have more of a mix. So that tells us that there are some areas on the deltas like the Yukon where we've got higher channel density and the smaller islands that are red, and other areas that have just these few large islands where there's less channel activity. And already we can see then just from this one metric, right, that there's some large morphological differences within these 6 systems, a few of them having all small islands and a few of them having more of a mix. Now, the distribution of island sizes, it's also important because it tells us something about the nourishment of ecosystems that inhabit these islands. And it also gives us some clues about the resilience of these areas in the face of possible sea level rise. So we know that areas that are closer to channels, right, they get more frequent overbank flooding. So there's more frequent delivery, areas closer to channels, of water, sediments, and nutrients. So this means that areas that overall have a higher channel density or smaller islands between the channels, something like this bottom drawing here that I did, these areas can better distribute fluxes to nourish ecosystems on the islands and also help those islands degrade to keep up with sea level rise. Areas, though, or deltas in general, that have a lower channel density or these much larger islands, they're going to have areas that are farther away from the channel. So they're harder to nourish, and it's less likely that sediments get delivered there with any sort of frequency. So this tells us then that the deltas that have all of the small islands, so like the Mackenzie, the Yenisei, and the Lena, these could be more resilient to sea level rise than the Colville, the Yukon, and the Colima that have some larger islands, assuming all else is equal. Now, in the past, people have looked, Doug Edmonds has looked at some temperate systems and the island size distributions there and showed that they have about 50% small islands, small here being normalized areas that are about 5% of the total delta area or less. But I'm showing you that there are some Arctic systems that have 100% small islands. So this could be a function of size. So most of these deltas that I'm looking at are pretty large and we're normalizing by the total area. So it's possible that that's just making all of the normalized areas really small. We can't rule that out until we have done some sort of more systematic comparison to other large deltas, which is what we are starting to do now. But it could also be that Arctic deltas actually have a really low sediment load compared to temperate systems. So Arctic rivers and deltas drain permafrost watersheds. They're largely frozen. There's not a lot of sediment supplied to the rivers, meaning there's not a lot of sediment available to the deltas to fill in small channels that are less geomorphically active. So that could preserve those small channels, which then preserves the small islands by default. It's an option, but the Mackenzie actually has the highest sediment load of these 6 deltas, and it's still showing all these really small islands. So that's probably not it. And this metric alone is certainly not going to answer the question for us. But since the channels control the depositional patterns, we can turn to looking at the channels to try to gain some insights on this island size distribution. And then the channels will also give us more information about those coastal fluxes, right? How the deltas are conveying, transporting, distributing water, sediments, and nutrients to the coast. Oh, my PowerPoint has crashed. Okay, let me open it back up. I'll talk a little bit while I'm opening it back up. So we're going to look at the channels using just one metric, which is actually a new metric that we developed explicitly for the purposes of trying to understand how evenly or how uniformly the fluxes get delivered to the shoreline. Here we go. All right. So we're going to look at this metric, which is called the evenness number. So it gives us this sense of how uniformly sediments might get distributed to the shoreline. Also gives us some insights about where nutrients might get delivered to marine ecosystems. So the evenness number really simply is just 1 over the coefficient of variation of channel spacing times 1 over the coefficient of variation of channel width. So if there's a lot of variability in the spacing of channels or the width of channels or both, lots of variability means not very evenly distributed. If we instead have less variability in these, then the fluxes are more uniformly distributed to the shoreline and to the coastal ocean, right? And so we're just going to compare the relative values of the evenness number. Its actual value doesn't really tell you anything. And we'll measure the quantities for this evenness number along this red transect. So this is an example I drew here on the Colville Delta on the right. This transect is a line that's parallel to the shoreline of the delta, but you'll notice it's set back a bit. So it can be really difficult to measure what would be a relevant channel width right at the shoreline. So to just avoid that complication and sort of the noisiness of delta shorelines in general, we set this transect back 20% of the total delta length to measure these different quantities for the evenness number. So here I've got the components of the evenness number for these 6 systems. So we've got the coefficient of variation of channel spacing on the left, channel width in the center, and then the evenness number itself on the right. And I've plotted all of these against the width of the delta at its shoreline. So this is some measure of the size of the delta, but it's also a measure then of the length of coastline over which water, sediment, and nutrients could be delivered to the shoreline and to the coastal ocean. So we'll start with this coefficient of variation of channel spacing. You can see that it seems to scale with the size of the deltas. So we've got the largest deltas out here, the Lena and the Mackenzie. They have a lot more variability in channel spacing than the other four. If you look in the middle, look at the variability in channel size or channel width, which here we're going to say is a proxy for flux. You can see that the variability is pretty high for all these systems except for the Colville. So in combination, then that gives us on the right that the evenness number is inversely proportional to the size of the delta, obviously with a few serious end members here. So we've got the Lena delta out here on the right. The Lena has over 220 kilometers of coastline over which it could be distributing water and sediments, but the evenness number is pretty low relative to some of the other systems. So the fluxes are likely not very evenly or uniformly distributed, especially compared to something like the Colville delta, where it does pretty evenly distribute its fluxes relative to the other five, but the shoreline length is really small, only about 20 kilometers. And so we can interpret this to say then that these 6 deltas at least seem to contribute their fluxes at pretty discrete locations along the coast. The smaller deltas, right, distribute their fluxes evenly, but the length of coastline is pretty small compared to something like the Lena delta, where it could be distributing it over a really large swath, but there are likely a few preferred pathways. So at a large scale, the fluxes are likely distributed at pretty discrete locations. I can show this in a different way for these end members of the Colville and Lena. So here we've actually estimated the fraction of river discharge, here just water discharge. So the fraction of river discharge that exits each individual channel mouth. And so we did this by just extracting the channel network center lines, some simple flux partitioning rules for all the different bifurcations. And so the size of the circles here scale with the fraction of river discharge exiting each channel mouth. And if you compare for the Colville and Lena, you can see that for the Colville, they're all kind of in this 5 to 10% range. There's a few 15s, but the distribution of circle sizes is pretty small. So the fluxes are much more evenly distributed on the Colville compared to something like the Lena, right? Where there are clearly a few preferred pathways that have these larger circles, despite this larger spatial extent. Now, what controls this flux distribution? So there's a couple different things that we have found to be particularly important for the 6 systems we're looking at. One is antecedent conditions. So we've got 2 deltas, the Yenisei and the Mackenzie, that grew in confinement. So the Yenisei I'm showing here on the right, this grew into a long, narrow estuary. The Mackenzie grew into an old glacial valley. And so these deltas are confined. That places an upper limit on the width of the deltas. Also likely has an effect on the development of the channel network as well. Then we've got a couple of deltas that actually have terraces within them. So this image on the left here is the Lena Delta, and you can see the upper left corner of it is this sort of orange-brown, splotchy looking area. This is called Arga Island, and it is not actually a part of the Lena Delta. It's an old fluvial terrace. It sits a few tens of meters above modern sea level. And there are a number of terraces throughout the Lena, and there are a few throughout the Mackenzie as well. And so these terraces then are an obstruction to the development of the delta. They're an obstruction to the development of the channel network because you likely cannot relocate a channel through a 20-meter high terrace, right? So these terraces actually drive the large variability in channel spacing that we see, and they just so happen to exist on the largest Arctic deltas, which are the Mackenzie and the Lena. So there's no causal relationship there between the delta size and the variability in channel spacing. It just kind of works out that way, and it drives that evenness relationship. Now, we also saw, though, that there is this large variability in channel width for most of these systems. And this is where I think the ice cover really comes into play. So this image on the left here, this is from mid-May 2013 of the Kolyma Delta. And at this point in May, the river hydrograph has just started to rise as the snow melt begins in the spring. You can see in this Landsat scene, there's a bunch of this bright blue, so ice and snow. And then there are these 2 main channels sort of on the eastern side of the delta that have started to melt out a little bit, where you see these patches of darker blue peeking out. Now, if you look a week later, the image on the right, you see that there is this third channel that has appeared. So this third channel has appeared now as the river levels have continued to rise, and this third channel was then able to melt its ice enough that we could see it in this imagery. There's also obviously more melting in the larger channels as well, especially at their channel mouths. So you can see that these larger channels then have been active for a bit longer. So they're delivering more water, they're delivering more heat to the coast that melts that overlying ice cover. But this smaller channel was actually blocked by ice up until this point. So this has been seen in the field and other systems as well, where you have these larger channels that are hydrologically and geomorphically active for a longer period of time than the smaller channels, because the smaller channels freeze all the way to the bed. They're pretty shallow. So if they freeze all the way to the bed, it takes longer for those small channels that are completely blocked by ice to be able to convey flow and for their ice to then melt. So if the larger channels then are active for a longer period of time, then we could hypothesize that over long time scales, those channels that activate sooner and stay active longer could grow larger, wider and deeper to accommodate more of the flow until those smaller channels melt out. So that would make the larger channels get larger over time, but it would also keep those small channels small because they're not very active. The ice then also helps to preserve the small channels on the delta, because if they're blocked by ice, right, they can't fill in with sediment. So I think that this feedback actually drives the large variability in width that we see for these systems. So if the ice is helping to preserve the small channels, then I think it could also be helping to preserve the small islands, right? So if the channels don't fill in with sediment, the islands don't merge, and that's one of the ways that those large islands develop during avulsions as channels relocate elsewhere. So if you maintain those small channels, you maintain that higher channel density and those smaller islands too. Now, these ice melting patterns, they also tell us now that there is some temporal variability in that spatial distribution of fluxes. So over short seasonal timescales, the way that deltas convey riverine fluxes changes depending on how the channels turn on and off with the changes in ice cover and the river hydrograph. Now, if we assume also that the sediment transport patterns roughly follow the channel patterns, then I think this suggests that there's also this non-uniform spatial distribution of sediment flux. So there are likely some areas of the deltas that are receiving more sediments than others, and areas then receiving lots of sediments, of course, could be more resilient to sea level rise because they have more supply. So if this is right, then I think this means that the ice cover is actually really important for the resilience of these systems, but also for controlling the water and sediment transport patterns and the distribution of fluxes. Now, the other aspect of these systems that's really important for understanding those transport pathways is actually lakes. So we don't often talk about lakes on deltas too often, but to show you how important they are, I've put on the left side of this screen a binary mask of just the channel network of the Mackenzie Delta. If I add the lakes to this mask, you get the image on the right. So that's a sponge, right? There's a lot of area here covered with lakes that could store water, that could alter the transport of water, sediments, and nutrients. And these lakes are actually a really clear signature of permafrost. So we've got a couple different lake types on Arctic deltas. We do, of course, see some oxbows and some abandoned channels that are largely disconnected from the active channel network. But these only make up about 10 to 15% of the lakes that we see. Most of the lakes are thermokarst lakes. And thermokarst lakes are a uniquely permafrost feature that form when water pools in any sort of slight depression on the landscape. That water then acts as a heat source that heats the frozen ground beneath it, eventually thawing the permafrost, so melting the ground ice, and that loss of ground ice results then in subsidence of the land. Subsidence then makes a larger depression, you can hold more water, holds more heat, and you grow this lake over time. So we have these thermokarst lakes that really cover Arctic deltas. And this lake coverage is what I'm going to start with here for looking at the lakes. This gives us this sort of first order estimate of the storage potential for sediments and also potential for things like biogeochemical cycling. So here I'm showing the total lake coverage on the Delta Islands. So the islands are black, the lakes are orange, and then all of the non-island land is gray. And you can see that the overall lake coverage is highest on the Colville, 25% covered, and the Mackenzie, 28% covered. So to first order, these systems, I would say, have the highest potential for trapping and storing suspended sediments in the lakes, which would then reduce the amount of sediment transport to the coast, reducing the coastal turbidity. These systems also then have the greatest potential for exchange of lake water with channel water, where the lakes could be a source of nutrients back to the system, or they could just aid in nutrient cycling. The other end of the spectrum here is the Yenisei. So the Yenisei is only 8% covered with lakes. So there's of course still things like overbank transport and flooding on the Delta Plain, but the lakes themselves are likely a less important part of the story in terms of being sediment reservoirs or increasing residence times that affect nutrient cycling. But not all of the lakes in these systems have the same potential for interacting with the channels. So if we want to assess the potential for storage and cycling, we can look just at the connected lakes. And the connected lakes tell us which lakes have consistent availability for storage and by geochemical changes. And I'm going to look here just at the structurally connected lakes. So the lakes that have a direct surface water link, even at these low water times that we're looking at of late summer. So structurally connected lakes could be directly connected to a distributary channel. They could be connected through a tide channel or chained together. And if I show you here just the end members, again, we see that the connectivity is highest on the Colville and lowest on the Yenisei. So in these images, I've removed all of the lakes that were not connected, and I've just left the connected lakes in green. So you can see that there's this really complicated now channel lake network on the Colville, where the lakes are likely playing a role in suspended sediment transport and nutrient transport. On the Colville, at least, and on the Mackenzie, but compared to something like the Yenisei, where there's not much green here, right? So there's not a big story here with the lake connectivity on the Yenisei in the way that there is in the Colville and the Mackenzie. And we can show this in a little bit more detail. So here I'm showing in this table, the connected lake areas on each delta, and it's highest on the Lena and the Mackenzie. Maybe not too surprising because those are the largest deltas. If we want to understand, though, the role of lakes in transport and storage, we need to compare these lake areas to some sort of relevant discharge, the amount of water that might be moving into the lakes. So here I've got the floodwater volumes in cubic kilometers, which is the average volume of water above some estimated bankful discharge. So it's the average volume of water that we think would be available to go into the lakes, the connected lakes alone at least. And if we use this floodwater volume and some sort of estimated lake storage depth of 1 meter, which is about the observed average lake level fluctuations in these systems in the spring, then we see that the potential for storage is highest on the Colville and the Mackenzie. Again, the actual number is not super important. We're just comparing the relative numbers between the 6 systems. So the Colville and the Mackenzie, they've got the highest lake coverage. They've got the highest connectivity. So they have the most complex transport pathways and the highest potential for consistently routing water and sediments into and out of the lakes that could result in deposition of suspended sediments, could result in nutrient cycling, or could actually be a source of solutes back to the channels and out to the coast. The Yenisei, right, that's a system where the lakes are less important. So if you want to understand the transport pathways through something like the Yenisei or possibly also the Colima, you could probably approximate that with just the distributary network and you do a pretty good job. But for something like the Colville and the Mackenzie that have these complicated connected lake networks, they could really alter the magnitude, timing, and locations even of coastal fluxes, could alter the depositional patterns within the delta in ways that we do not currently account for when we try to estimate fluxes moving through these systems and when we try to estimate sediment transport patterns. But this analysis doesn't tell us how that connectivity or storage potential really varies over a spring flood. So in spring floods, we see a lot of overbank flow, like on this image of the Yukon Delta here, a lot of overbank flow that inundates much of the surface. So it doesn't tell us, our current analysis doesn't tell us how this hydrologic connectivity changes over these short seasonal timescales, or over longer timescales as the permafrost thaws, right? And as the Arctic warms. So we'd expect that as the permafrost continues to thaw and degrade, you'll see more lakes developing in these systems, more lakes connected to the channel network, meaning the lakes are likely to become an even more important component of Arctic delta dynamics moving forward. And this really points to the idea that delta form and function are dynamic, right? So we're only looking right now at the present day morphologies of Arctic deltas. And we can use those observations to make some hypotheses about landscape form and function, but we see these changes over both short and long timescales that are not captured here. So we've got seasonally varying hydrologic connectivity. We also see those seasonal patterns of ice retreat that affect which channels are active at any given time. We know that there are going to be these longer timescale changes as the landscapes evolve, as their drivers and controls evolve, and we're not really capturing any of that in this snapshot in time. We also can't really understand the processes that shape the deltas and how those processes are influenced by the presence of ice and permafrost. So if we want to look at the delta forming processes and these ice and permafrost effects, we can turn to some modeling. So this is modeling work that we've been doing with this reduced complexity model, Delta RCM. This is a model of delta morphodynamics that was developed by Mon Liang during her PhD. And it is a cellular model that operates on a directed random walk that's weighted by water surface slope topography and inertia. This model assumes bank full flow. So we're only going to model about 10 days a year that are the most, we think, geomorphically relevant days. And for Arctic systems, this is actually a really good approximation. So like I said, they're frozen for 7 to 9 months of the year, not a lot of action happening there. And then the spring flood that dominates a number of these systems, it's really short. It's 1 to 2 weeks, really, and that's when a lot of the activity is happening. So assuming bank flow and modeling about 10 days a year is a pretty good approximation. The model is capable of generating and recording stratigraphy. I'm not going to show you stratigraphy today, but I like to mention it because it gives us a really easy way to track the ages of deposits in this system. And if we can track the ages of deposits, it gives us an easy way then to track how permafrost develops over time, because permafrost, remember, has to be frozen or has to be below 0 degrees C for at least 2 years. And so we add to this model rules for how ice and permafrost affect the routing of water and sediment parcels through the model domain. So for permafrost, we add in this effect that permafrost is harder to erode. And this comes from some remote sensing observations that my colleague Joel Rowland has been doing, looking at riverbank erosion rates in permafrost versus non-permafrost systems. So he's finding that permafrost riverbanks erode more slowly, and we think that this happens really because of the presence of ice. So here I'm showing a permafrost core that we took from the floodplain of the Koyukuk River in Alaska, and you can see there's a number of ice lenses within it. So if there's ice in the permafrost, then you first have to melt the ice, thaw the permafrost, before you can mechanically erode the banks. So it's going to take a bit more time than just mechanically eroding the sediments. So in the model, we translate this into permafrost having a different erodibility than non-permafrost, and we make it be some fraction, some percentage less than 1 of the non-permafrost value. So there's a velocity-based threshold in the model, which we divide by this permafrost erodibility to increase the threshold then for erosion of permafrost relative to non-permafrost. And we also have a lower rate of lateral diffusion as well. So there's this lateral redistribution of sediment that occurs that's proportional to the local slope. But again, we just multiply it by this lower erodibility so that we have less lateral sediment flux. And this allows us then to build up steeper permafrost banks, which we often see in the field. We form permafrost in the model gradually as the delta evolves. So we track the ages of deposits, how long they've been beneath some depth of seasonal thaw, which is the active layer. And basically, as soon as a deposit has been beneath that depth of seasonal thaw, which we set to 0.5 meter for at least 2 years, then we flag it as being permafrost with these effects on transport turn on. For ice, we're only including the effects of shorefast ice. So shorefast ice or ice that's attached to the shoreline or the riverbanks, tends to constrict the flow. And so we pull some observations from other people's field and laboratory data to include this effect in the model, where we have ice that can exist over any water, and it starts at some prescribed distance up the delta, which we typically set to about 40%. That comes from some remote sensing observations of like the ice extent during the time of peak flow. The ice then melts throughout a flood. So we've got some background atmospheric rate that's uniform in space and time, but we've also got this velocity weighted melting. So the rate of change of ice thickness is proportional to a bunch of heat constants, but also this local velocity. So higher velocity is going to melt the ice faster. And then we have this flow constriction. So the ice reduces the flow depth by its thickness. And we have here a 5-meter deep receiving basin in the model. And so we've got ice thicknesses ranging from really thin surface ice of 0.5 meter up to really thick ice that's almost as thick as the basin is deep. So 4.5 meters in a 5-meter deep basin. And then the ice increases the resistance to flow. So we have this resistance term in the model for selecting where water and sediment parcels end up going. And you can see that it's inversely proportional to the effective depth, which is reduced by this ice thickness. And so this resistance term is meant to represent something about the additional friction now in the channel associated with the underside of the ice. So here's an example of one of our experiments. This is the medium permafrost erodibility and medium ice thickness. And in the upper left, you can see the topography developing over time. The lower left is discharge. The upper right is ice thickness. And the lower right is just a binary permafrost map. So black is permafrost and white is not permafrost. So all these systems, we're just doing that 10-day bankful flow in the year. We have the same active layer thickness as well of 0.5 meter, active layer, that depth of seasonal thaw. And then we also run the model first for 300 time steps without those Arctic effects, without the ice and permafrost. So that lets us develop a channel network before we start perturbing things. Now this video in the upper right that you see kind of flashing at you, so that's the ice thickness. So remember, the ice starts at some maximum extent and thickness and then melts throughout a spring flood. So you have the maximum ice when you see all of the white, and then you see it melt within the channels and at the channel mouths over the course of the spring flood. And then it snaps back to its maximum extent. Then in the lower right, we've got this permafrost map, and you can see that the permafrost is pretty well tracking the topography, which sort of makes sense, right? You have thicker, older deposits, more likely to be permafrost than the newer, thinner deposits. We're not forming permafrost, though, under the channels, which is good. So active channels and relic channels, like those lakes I talked about, they're a heat source, right? So you're not likely to develop permafrost right under the channel. You often have a thawed area right under the channel, but you do develop permafrost sort of around the channel banks. So similar to the remote sensing, I'm going to walk through just a couple of metrics that give us some insights about what effects ice and permafrost are having on these systems. And the first thing that we really noticed in looking at these experiments is that both ice and permafrost limit channel mobility. Now, I think this is expected for the permafrost because we imposed that change in erodibility, but it's not as expected for the ice. So on the left here, we've got these maps showing the fraction of time that any area in the model was a channel for a case with no ice and no permafrost on the top, and then the maximum ice thickness and minimum permafrost erodibility in the bottom. And if you compare these maps, you can see that there are much more intense blues in this bottom image than the top. So the ice and permafrost here, they really locked these channels in place. On the right, this figure is showing the relative channel mobility as a function of permafrost erodibility, and we've got the different ice thicknesses in here too. And in this case, the relative channel mobility, this is just the rate at which channels move to new locations and abandon old locations. What you can see here is that the channel mobility is clearly sensitive to both ice thickness and permafrost erodibility. But for this thickest ice in orange, or the most resistant permafrost here of 65%, the reduction in mobility is so strong that it doesn't really matter what the other condition is. The channels are just really stable with either of those conditions on their own. Now, the ice seems to limit channel mobility because of that flow constriction. So you have constriction of the flow underneath the ice that scours out the channels, that also prevents in-channel deposition. So that means that the channels stay as really strong flow attractors in the model, and they get preserved then for a really long period of time that makes them really persistent. And if you combine that with the decreased erodibility of permafrost, then the ice and permafrost are just really effective at stabilizing the channel network. So thinking forward then to this future warmer Arctic, the channels are likely to be more mobile with the loss of ice and permafrost. So we'll see faster reworking of delta deposits, more sediment delivery to the coast, and more carbon delivery to the coast from these really carbon-rich permafrost delta deposits. Now, one consequence of this increased stability is that it changes the overall depositional patterns on these deltas. So here I'm showing you maps of topography, but we've detrended the topography by the background slope, so it's easier to see the areas that are higher or lower. And I've got just the end members here for the maximum ice thickness and the minimum permafrost erodibility compared to a no ice, no permafrost case in the upper left. Now, in general, we see that overbank deposition is increased with the presence of ice, particularly thick ice. So ice has a tendency to encourage more overbank flooding because it elevates the water surface upstream of the ice cover. So we have this sort of enhanced backwater effect. So with deltas with ice, then, we see that there are more areas in these greens that are higher elevation and fewer areas in blue that are lower elevation areas relative to this case with no ice and no permafrost because of that more frequent and more extensive overbank flooding. With the permafrost, since the permafrost is so effective at stabilizing the channels, we actually see higher levee deposits in these systems. So the permafrost helps to create these higher levee-like deposits that then further locks the channels in place. And if you add to that then ice, then we see this effect is more pronounced because of that more frequent and more extensive flooding. So we get even higher levees that are more broadly distributed across the delta. So the spatial distribution then of overbank aggradation, it differs depending on whether you have ice or permafrost and what those ice and permafrost conditions are, but the effect is somewhat similar. So both of these conditions of ice and permafrost seem to help deltas aggrade more quickly. So the loss of ice and permafrost then in a warmer Arctic could make these systems more vulnerable to sea level rise if the aggradation rates decrease. The caveat here, right, is that the enhanced levees with permafrost, they actually limit the extent of overbank flooding. So if you were to just lose permafrost alone in the future, that could make aggradation easier. But if you lose both ice and permafrost, which is what will likely happen, right, that's going to reduce the overbank aggradation. And this effect of ice, in particular, to alter the large-scale depositional patterns, it's not limited to the terrestrial realm. So we actually see effects as well in the nearshore. So this plot on the left here is showing the fraction of the offshore area, so the subaqueous part of the model domain that's past the delta shoreline, the fraction of the offshore area that's incised by channels as a function of ice thickness. The figures on the right here, these are just topography maps again, where you can see for different ice thicknesses what the topography looks like, and you can see some offshore incision here. So as the ice thickness increases, you see that the amount of incision in the coastal ocean increases, and permafrost has no effect on this. This is just an ice cover effect. So we can get up to 15% of the offshore area in the model that's incised for the thickest ice, and pretty much no incision for thinner ice, a little bit, I guess, for the medium. If you look at the maps on the right, you can see that this incision occurs where the channels extend beyond the shoreline. So they extend out into the coastal ocean, where the ice cover constricts the flow, driving the scour that extends the subaqueous channel network. These channels carry sediments with them, right? So as this subaqueous channel network develops, we also develop then these abundant subaqueous deposits. So for the 3-meter thick ice, you see that you've got these deposits, but they're kind of close into the shoreline. They're pretty thick though, they're up to half of the basin depth. For the thicker ice, the deposits are more spatially extensive, but quite a bit thinner. And these subaqueous features that we're now seeing at the delta front, they're really similar to what's been observed in natural systems as well. So this figure on the left here, this is from a report by Bill Dupree, where he mapped the extent of this sub-ice platform on the Yukon Delta and showed that many of the channels that we can see subaerially actually extend beneath the water surface, incised into this shallow subaqueous ramp. So these channels now funnel water and sediment farther out into the ocean. So we're producing in the model some similar features, I would say, and some similar depositional patterns that tell us that this is likely a signature of ice cover on the morphology of Arctic deltas. Now, in the last few minutes here, I'm going to turn away from these longer term, larger scale things we've been looking at in the modeling, and I want to return to talking about those shorter seasonal timescale dynamics, because we saw in the remote sensing that the ice could have this effect on the short-term channel activity that might drive this longer timescale effect on channel and island sizes. And so really quickly, I'm going to show you one more result. Here I'm showing you, again, the fraction of time that each cell was a channel, but now we've got a time series of 4 consecutive floods instead of over the entire model run, which is what I showed earlier. So the top row here, no ice, no permafrost. Bottom rows, thickest ice, different permafrost irritabilities. And if we look at the top row, you can see that most of the channels are yellow for these first few floods. So they're active for the entire length of the flood. But if you look across numerous floods, you can see that the locations of the channels start to change and you develop new channels by the 4th flood or the 4th year. If you look at these ice-covered runs, though, in the bottom 2 rows, you can see that the locations of the channels are much more stable across the 4 floods. But within an individual flood, we see a lot more variability. So there's a lot more of these greens and blues. There's some of these really faint channels out in the distal part of the delta. So with the addition of ice, we now have some of these smaller channels that are active for only part of the time. They're typically active later in the flood. And there are a number of larger channels that are active for a longer period of time. And hopefully this is sounding a little familiar because this is what we saw in the remote sensing observations as well. So I'm going to argue that this is the signature of ice cover, where ice creates this size-dependent channel activity that drives some size-dependent channel persistence and helps to preserve the small channels and the small islands. So remember that we saw a number of these larger Arctic deltas that have lots of small islands. This plot on the left here is now showing distribution of island sizes, but from the modeling. So we've got a case of no ice and no permafrost with the green dashed line and the different ice-covered runs in the blues. And what we see is that the ice-covered experiments, they lack this large tail of the larger islands. They have a narrower overall distribution of island sizes, and it's slightly shifted towards smaller sizes. So we think that the ice helps to maintain this higher channel density by preserving small channels, thereby creating smaller islands. So as the Arctic warms, we might expect then that a reduction in the ice cover could make these smaller channels fill in faster. That would reduce the number of transport pathways to the coast and create more of these larger islands that makes it more difficult for deltas to keep up with sea level rise. Oh, well, my PowerPoint crashed again, so I'll just say that that's the end and bring up my conclusion slides. And if people want to start asking questions, please feel free.
Anastasia, thank you so much. Maybe you also can bring back your PowerPoint when
Yes.
people ask a question. This is a fantastic talk. And we are looking for this kind of talk for a while. Finally, we have you to talk about Arctic river and delta. Really, really great. So let's say, let me enable unmute. So if you have any question now, you can unmute yourself and go ahead to ask her. So Anastasia, let me have a quick question. And so see if any other people have any question. So if we look at all the high latitude river delta morphology, looks like they have a very common similarity in terms of the buffer, in terms of the distributary channels. And so what's the reason caused it? Is this ice cover is play a major role? And It's not a river dominated, wave dominated, or tide dominated. It's not kind of not driven by that.
So you're saying you think that all the channel networks are relatively similar?
I mean, if you look at all the way from Yukon, Lena, even Salinger, last week, Tian talked about Salinger River Delta. So why they look so similar? I mean, morphology.
So I would argue that they don't look similar, I guess. So I reject the premise of the question. So, I think that they all look pretty different. And that's part of the problem. I mean, I think there are some ice signatures on them, perhaps. So we think that there's this effect on, the preservation of small channels for sure. But I mean, if you just look at these 6 systems that I've got up here, you've got 2 that are kind of more fan shaped. You've got these 2 really elongate systems with more anastomosing channels. And then you've got these 2 deltas, like triangles, actually, right? Where they're sort of more close into the coast. So maybe they're kind of grouped, but I'm not sure that I would agree that they're all necessarily having similar channel networks.
That's very good. Okay, I have another question, but let's wait. Let's give it to James. Hey, James, go ahead.
Hey, Paul. Hey, Anastasia, thank you. That was just a fascinating talk. I was going to ask you, when you look at the morphology of the channels on these deltas and you compare them to sort of non-permafrost deltas, do you see the presence of crevasse splay type deposits as much in these Arctic deltas as you do elsewhere? I'm just wondering whether this importance of the ice cover that you're saying, does it limit crevassing and that type of process in these channels compared to more temperate deltas?
Yeah, that's a really great question. So I would say we're really early in our temperate delta comparison, so I can't answer that confidently. But what I will say, right now we're looking at Landsat. So I'm not sure that we're going to resolve some of those crevasses anyway, but I agree with your thinking that the permafrost may limit the amount of crevasse splays that you see in these systems. We do see some really drastic erosional features that pop up from permafrost in these systems, or from ice rather, not from permafrost in these systems, but not a ton of crevassing as compared to temperate systems. So I agree that I think that that's likely there. We likely need higher resolution imagery to see that difference.
Because one of the corollary of that is if that's the case, whether then it takes out crevassing as a way of actually diverting channels and giving more mobility to network than those really stunning plots that you showed where you've got more stability.
Yeah, I agree. I think that that's probably part of what happens. And, we do see plenty of pretty sizable tie channels, tie channels that we're resolving at 30 meters in these systems. That certainly connect to the lakes. But we do know from the couple of times we've pulled the higher res imagery, we're missing some of those smaller channels, but not a ton of crevasse splays. Yeah.
Okay, thanks. Hey, thanks. That was a wonderful talk. Thank you.
Thanks.
So, Anastasia, this is James' question also related to my second question. And if anybody look at the river discharge, annual discharge, and the relationship with this high latitude river delta, the Siberia delta size, compared to the tropical river system. And this is the question is about the retention rate. The retention, I mean, is when the river sediment coming down, how much left to build the delta plan, how much escape to the underwater subaqueous. So is there any difference that's high latitude compare the low latitude? For example, the Wax Lake Delta in Louisiana, that looks like here, a couple. So is there any that kind of, do you know?
Yeah, it's a good question. So overall, the sediment loads to the Arctic deltas are much lower than their temperate and tropical counterparts. And so the supply is less, and yet some of them are giant, right? So clearly there's a fair bit of retention within the Arctic deltas that's going into building these landscapes. I mean, the Lena Delta is enormous, and it's got a pretty low sediment supply compared to lower latitude rivers that have a similar river water discharge. You're right that we are losing some sediments to that under ice funneling, and that build up instead a much larger subaqueous platform. But I think on Arctic deltas, we see quite a bit more overbank transport that contributes, yes, to vertical aggradation and also to some extent to shoreline progradation as well. And so it's possible that there's sort of a balance there where you have an increased rate of flooding just because of the flashiness of the hydrographs and the presence of the ice that encourages that maybe compensates for some of that loss under ice.
That's interesting. Maybe we can talk about later. If nobody have already done that, maybe we can ask one student to pull all the data, do a comparison.
Yeah, so we've pulled some of the water data. The sediment is a little harder to tease out. I think Yap is on here, so he did pull some like WBM SED estimates for them to try to compare. So yeah, we could definitely chat about.
Yeah, we can. Okay, John. Is John
Shaw?
Yeah. Hi. Yes. So cool to see this presented. I've been really enjoying your papers especially your 2021. My question. So I looked at your models and they seem dynamic and like a lot of channels shooting here and there, and that's sort of a nature of modeling a small delta. But again, they look very dynamic, and I get an impression, at least sedimentologically, that these channel networks that you show up here are kind of frozen and they're not moving that much. But do you have some intuition about like? Are they changing? On the Mackenzie where you have all those hundreds of channels, are they like soft avulsing here and there? I'm not asking for data, but do you have an impression of that?
Yeah. So okay, I'll answer your question in two parts because you brought up soft avulsion, which is a different interesting thing. So are they changing in general? Yes, very slowly. So we did pull some like 1980s Landsat imagery as well to try to look for like rates of migration. And obviously, at a bend, you see quite a bit, right? But for most of these systems, it's non-detectable at the resolution of Landsat over most of the landscape. You might get 1 to 2 pixels of movement in a 20 to 30 year period of time, and 1 to 2 pixels is like our uncertainty for telling you where a bank is, right? Like banks are really hard to identify. So they're moving very, very slowly. They're frozen, right? So that's not terribly surprising. The soft avulsion thing is a little different. And I think that, the this like ice retreat pattern affecting which channels turn on and off, I think is basically, I would call a soft avulsion, right? Where you have a redistribution of water and sediment within the channel network over really short seasonal timescales. And obviously it's not gonna, this is my soft avulsion. So it's not gonna happen in the same way in every single year. And so it's likely that that might change over time. We started to pull imagery for this, or SAR, actually synthetic aperture radar, a year ago to try to look at whether or not that rate of ice retreat and the spatial pattern of it changed over time. And that would give us an indication of how the soft avulsion was evolving and whether or not one channel might become more dominant than the other. So I think that's a way you could start to look at that over sort of a decadal timescale with the availability of like Sentinel. But we haven't found anything yet.
Very, very good. Okay, that's really fantastic. So is any other question from the audience? Oh, okay, Yijun, go ahead.
Hi, I really enjoyed your talk. I really do. It's very interesting to see the system response to basically frost, permafrost, and ice. I was wondering if you have a pair or more pairs of images showing the development between a very cold year and a very hot year, so very warm year, say using non-frozen days as a parameter to compare the dynamic under a very hot year and a very cold year. I was just wondering if you have compared satellite images between these two very different weather conditions.
So we haven't. There is, so in the Arctic in general, really in all parts of things that control deltas, there's a lot of interannual variability. So it's an interesting idea. We certainly could try to compare images. I think the issue that would arise, again, would be related to the resolution. So because it sounds like you're asking about whether or not the dynamics are different within a single hot year, right, versus within a single cold year. And I'm not sure that you'd be able to tease anything out from remote sensing based imagery, even if you had like 5-meter resolution imagery. I'm not sure you'd really tease too much out within a single year because they still do change so slowly, even if you have a particularly warm year.
Yeah, sorry. Yeah, go ahead.
No, that's okay. Go ahead.
So my thought is, during a very hot year, you would expect a higher runoff, early slow melt from the drainage basin. Mm-hmm. And you would have a higher flow and higher transport also to the system, to the mouth deltaic system, versus a very cold year where ice and plays a huge role. And so, I mean, that data could be obtained from National Weather Station. So just to see the weather over this drainage basin, I guess I'm not familiar with the Arctic system. I guess you don't have probably very good solid discharge data from the river, do you?
No. Well, river discharge, yes, not sediment.
Yeah. Okay. Yeah. So my thought is that to see how different under two drastically different weather conditions. Yeah.
Right. Yeah. So we do, just in terms of the river discharge and the river hydrology, you do definitely see differences in the magnitude of the spring flood and the timing of the spring flood based on temperature and also snowpack. So it's not even just temperature, right? It's also related to the snowpack from the previous winter and the distribution of permafrost and the amount of time it takes water to get through that drainage network. So you do see certainly interannual variability in the river hydrology that we can pull out from the discharge records, absolutely. And so I think, in terms of looking at imagery that would go along with that, if you can get images that happen to occur during the spring flood, which for multispectral is always a guessing game, then maybe you could see differences in like the extent of flooding. I think it's just been difficult for people to capture with the return times of satellites.
Thank you. Mm-hmm.
Sure.
Very good. And that's very good. Okay, I think the final quick question. Anastasia, you show the model animation. Are you using Delft 3D or any other model to do that?
So right now we're using Delta RCM.
Delta RCM.
Mm-hmm.
Okay, cool. That's very cool. And so, okay, if no any other question, I think we can stop here. And I think this is a really, really great talk. And it's also archived all the way online on our YouTube channel. And so that's cool. Is John still there? He left. Okay. I talked to him. Okay. And Anastasia, thank you so much.
Great, thanks, Paul.
Fantastic. Great.
Thanks.
Okay, let me stop the live stream here.